Hello everyone. So in this video we're going to learn more about surface integral. So let's look at the outline first. So in this video we are going to talk about surface integral. Alright, and you will see that surface integral can be found in two different methods most of the time. So we are going to explore that today. So we're going to look at method 1 and method 2. So we're going to have like a few different situations or conditions in which surface integral is going to be applied, and we will look at the formula which is quite consistent across method 1 and method 2. Alright, so what are the situations or the conditions that we're going to look at today? We are going to look at finding surface integral in a scalar field, and of course after we are familiar with this, we're going to look at finding surface integral in vector field. And just before we delve more into this, which is the vector field, we will realize that in the formula itself it actually uses a unit vector normal for vector field. So before we're going to talk about this, we're going to park one in, which is unit vector normal. But I think you should be quite familiar with it already, right? Since we have sort of discussed this in somewhere the first part of our second part of the course. So this is what we're going to talk about today, and of course we're going to show you some examples after that. So let's start with surface integral. Alright, so what do we mean by surface integral? So imagine we are going to evaluate integrals where the point from surface is actually in 3D. So that's basically what we are sort of interested in. So imagine that we have this kind of surface. Alright, if I want to get surface integral, and by now most of you would have known that when we integrate an expression or equation, we actually are getting the area under the curve, if you still remember some basics of your maths. So how do we get surface integral? So we have this surface area bounded by this geometry here. Alright, so what we're going to do is that we are going to get the surface area by actually splitting each of these. Alright, so we are actually splitting these surfaces, alright, into very small tiny surface element. Alright, and let's say if this is actually by this side here is actually indicated by vector A, and this side here is actually indicated by vector B. Alright, so the ds, alright, s just to indicate the surface, will actually be equivalent to sort of like our parallelogram. If you remember how we get the area of our parallelogram, we actually use the cross product, isn't it? So it will be A dx cross B dy. Alright, so this is literally just to show you the gist of how it actually came about. Alright, and in your lecture note you will actually see some derivation of it and all, but in the end I'll just write down the simplified version here. What we're going to get is that it's going to be equal to 1 plus bracket of your df over dx square plus df over dy square dA. Alright, this is the square root. And of course, dA in this case, that's actually according to our area, right? So in this case, since we are talking about dx and dy, we're going to put it as dx and dy. And of course, by this dA here, it basically also means, and we're talking about surface integral anyway. So we are going to really look at double integrals in this case. Alright, please know that dx dy will not be fixed. it will be according to what you actually have or what's given in your surface or where your object or your surface actually lies in. So if let's say it actually lies in the plane of YZ, then it will be dy dz instead. All right. So if we are talking about ds, and ds is given by this, and let's say you actually have a function of z, all right, and it is expressed in terms of x and y, all right. If you see this case here, then therefore, here comes the formula. Our surface integral will just basically be the double integration of my, can you guess it? So it will be exactly the same as whatever that you have got here earlier, right? Because this is actually ds. So if you actually just do a double integral, you're going to get the s. So that will be my surface integral. So I'm just going to write this down again. Square plus df over dy square. And I'm going to write this in terms of the general form. So this will be dA. I'll just write this down clearer for you to see. And in certain lecture notes and all that, you will see that, well, sometimes they denote this as S. Alright, so S just indicates the surface. Sometimes you see it as D. So fret not. Actually, when you see D, it basically just sort of means that what you have been doing is that you're splitting all these small surfaces, alright? And therefore, when you sort of impose this surface, if you're splitting everything really, really small and you're going to impose it like a shadow, so this base here will be something that you see like a square shape here. So this will actually indicate the shadow, and it actually sometimes is indicated in D. It's actually in your lecture note, but fret not too much about this D or S over here. So that's just what I'm trying to tell you. So that's one. So this would be what we know as the method 1. Alright, I'm just gonna highlight this. This is the method 1 that we talk about. Alright, remember earlier we to say that we actually have 2 different methods, right? So let's explore the second one. And later I will also give you a question, and this question is actually in your example in lecture slide, and I'm going to actually explain it in another video so that you can actually just click on it whenever you want to look at it. So this video is really just about summary of what this topic is about. Alright, so you have a gist of what you should know about in every subtopic here. So we have got our method 1 already. So let's look at method 2. So method 2 is usually what we know as the parameterization method. Alright, so if you recall from what we have discussed in your lecture, parameterization is sort of for you to take points, alright, in a different vector. Let's say we take this vector in terms of u and v. So we take these points out of the 2D space and then we plug it into the vectors. And what is usually good, and when do we usually like to use parameterization? If you see method 1 earlier is kind of easy when you come across questions that are more straightforward, which just involves the Cartesian plane, which in this case it means your x, y and z. As for method 2, which is parameterization, remember besides Cartesian coordinate we have polar coordinates. So sometimes we can have surface integral questions that are based on cylindrical shape, sometimes on spherical shape. So this will be the case where you want to really reflect on again, and then you want to see whether it will be easier for you to use parameterization. Usually parameterization, this method 2 here, as I will show you later, it will be used mostly on cylindrical shape and spherical shape. But that doesn't mean that you can't use this shape and solve these shapes surface integral using method 1. You can still do that, only that at your dA later you will need to actually convert it into its equivalent polar coordinates. Yeah, because you know, for cylindrical and spherical shape, your polar coordinates is just not necessarily just x, y, z. You need to change it to your r cos phi and so on. All right, so let's start with my second method. Second method would be, since just now I said that we actually take a different points out of the 2D space. So let me just show you. If I am going to have my vector that is expressed in terms of u and v, I already use x and y here, so I'm just going to differentiate it using this. So it's going to be expressed in terms of this case here. So my x will be expressed in terms of u, v, I, y plus y, u, v of j, and plus z, u, v of k. Alright. And how do I find my surface integral? That will be my s. And again, as usual, you see a double integral there. And what happens is you will take your r of u cross r of v, and then you will get the magnitude of this. Alright, so the first vertical line that you see here is actually the cross product of your ru cross rv, and the second vertical line that you see on the outer part, that actually indicates the magnitude of it. Alright, this looks like a simplified version, but I will also show you. So this is for method 2. Alright, so let's explore what does it mean. Alright, so I have two different cases here. One could be the cylinder. Remember when we looked at polar coordinates earlier on, how do we express our x in Cartesian coordinate? Actually express it in terms of r cross phi, isn't it? And for my y, I actually indicate it as r sine phi. And z, if you want to guess for a moment, it will just be a z. Alright, and of course, when you have spherical shape, this one gets longer. So your x is what? Your s is r sine theta cos phi. Alright, well, y is r sine theta sine phi. That's correct. And your z is r cos theta. Alright, so what does it mean by this r here? I have a simplified version so that you don't get confused. In this case, your r revolves around your phi and your z for cylindrical shape. So what it basically means is that you're supposed to be finding for your dr over d phi, for this dr over dz. Alright, and therefore your ds will actually be equivalent to the cross product of your dr d phi cross dr over dz and the magnitude of it. Alright, and remember, this one is actually, if you refer back this to this method 2 here, alright, you can see that this is actually dA, isn't it? So for dA, you look that over here we are actually concerned with, it will be equivalent to my phi and my z, and therefore this will be my d phi dz. Alright, so you can use this formula, and of course if you want to get the s, the surface integral, you just get a double integral of it. So this is kind of like a general formula that you can use for cylindrical shape. And again, the same thing also applies when you go for spherical shape. In this case, you actually have the theta, and then after that you have the phi, right? Same thing goes, you find the dr over d theta, then you find the dr over d phi. Can you guess it? It's exactly right. So if I'm just going to write it down here, yeah, so my ds, I'm just going to write it right down below so that it's kind of easy for you to look at it. Then you see it, right? This is just dr over d phi cross dr over d theta. So basically you get a derivative of it, of your dr with respect to d phi, and you cross it with dr over d theta. That is the first vertical line, and after which you actually get the magnitude of them. Alright, so I hope you still remember how to get your magnitude. So which means you actually square each component and sum it up and get the square root of it. And for your dA here, as you guessed correctly, one tip is to look at the denominator. So it will be of d phi d theta. Alright, so this will be the one that you can use, alright, for your spherical coordinate, for spherical base shape. Alright, so if you look at lecture slide for example 1, you actually have an example of finding the surface area, alright, of a sphere. Alright, I'm just going to write it down here. Example 1, you want to get the surface area of sphere with radius of, sorry, I have to just, with radius of A. Alright, so we are going to explore how we use these two different methods earlier, alright, to solve this question. And I actually will do this in the other video. So if you want to look at how we actually use this formula for the method 1 and method 2. So method 1 here for the orange one, and method 2, parameterization, depending on which shape you're talking about. The top one here is for cylinder. This one is for sphere. Alright, so we're going to try this out in both methods, then you can compare which one is easier. Alright, and that will be in the other video. If you want to look at it now, you can just click on it on the other video.